How would you geometrically multiply two numbers? With a rectangle maybe? How about this? Take the standard parabola y equal x squared and make one of the numbers negative. Then lift both of them straight up to the parabola. Take the line connecting these 2 points and intersect it with the y-axis. The point on the y-axis then sits precisely at height a times b. I'm Bernhard Werner, this is Sum and Product, and in this video we will look at 2 geometric tricks involving placing points on a parabola. To start, let's prove the statement we see on screen. We write down the coordinates of the lifted points. Every point on the line connecting them can be written as the sum of one of them plus an appropriate multiple of the vector connecting them. All we now need is to find the right scalar multiple to land on the y-axis. We get that by setting the x-coordinate to 0 and solve for t. Then we plug this t value into the formula for the y-axis and, indeed, we end up with a times b. Now, while this might not be the simplest way to calculate products of numbers, you can build this quite easily as a physical calculator. And there is a very deep connection to projective geometry here. Alas, it would move us away from the idea of lifting things onto a parabola, so I will just leave a source in the description. Here I want to continue by exploring how this lifting might look if we go one dimension higher. First, what is a 3D parabola? Well, when we write down the similar looking formula z equal x squared plus y squared, it gives rise to a so-called paraboloid, which you can think of as a parabola rotated around the z-axis. That leaves the question of what exactly we want to lift to the paraboloid. Let's recall what we did in the 2D case. Given a parabola, we lifted 2 points up and then considered their connecting line. Reversely, we could have started with the line cutting across the parabola and then think about the relation between the points where it intersects the graph. This later idea is a bit easier to carry over to 3D. Here, we intersect the paraboloid with a plane. The intersection is some sort of quadratic curve, since we intersect something quadratic with something linear. These shapes are also known as conic sections, since you can get all of them by intersecting a plane with, well, a cone. In our case, this intersection will usually be an ellipse. 2 special cases to take note of though. If the plane is vertical, the intersection is actually a parabola. And if the plane is perfectly horizontal, we get a circle, which has nothing to do with the paraboloid itself. The same happens with any surface that is rotationally symmetric around the z-axis. But we want to look at a generic case of a slanted plane resulting in an ellipse. What shape do we get when we project it down onto the xy plane? In other words, what does its shadow look like? If we move the plane around, we can try to see anything special. But since we look at it from an angle, it just looks like an ellipse again. But if we look at it directly from below, it looks more like a circle. And it is. No matter how we cut the paraboloid, as long as the plane is not vertical, the shadow of the intersection is always a perfect circle. Obviously, it's difficult to see anything else properly from this perspective, so let's move back up. At first, the statement might seem quite remarkable, but the proof is surprisingly easy. We already have a formula for our paraboloid. And since we are only interested in the cases where the plane is not vertical, we can write down an equation for the plane in the form of z equal to something linear in x and y. And since both lines express how the z-coordinate behaves, we can set them equal. After moving everything to the left, we have this quadratic equation here. Now, if you have some experience in projective geometry, you might just know that this is what a circle equation looks like. The more recognizable form is this here, however. It basically says that the distance to the center M has to be the constant value r. You know, a circle. With this in mind, you can either complete the square to get from our equation to the standard circle formula, or you expand the bottom formula and compare coefficients. In any case, you will end up with something like this. Not only does this prove that the xy coordinates of the intersection form a circle, it also tells us how the center and radius of the circle can be calculated if we have the plane equation. With that, we can go back to the initial question of what we can lift up to the paraboloid and what it means. If you take 3 points in the xy plane, you can lift them up to the paraboloid and then look at the plane defined by these 3 lifted points. It intersects the paraboloid in a shape that, if projected down again, is the circle through our 3 initial points. Now, this is obviously not a particularly useful way to construct a circle. What I love about the statement, however, is the following. The simplest geometric construction you can do with 3 points in a plane is to build the circle through them. The simplest geometric construction you can do with 3 points in space is to look at the plane through them. And here we can observe that these constructions are effectively the same. To push our result a bit further, all points on the paraboloid below the plane correspond to points inside the circle, while points above the plane correspond to the outside. This has yet again little to do with the parabolic shape itself, but with the fact that we have a convex function here. Since we will need the concept of convexity anyway in a moment, let's look at the basic ideas here real quick. First, a set can be convex. That means if you take 2 points in the set and look at a straight line segment connecting them, all of these points in between also lie in the set. If we give the set and the points names, we can formalize this via this weighted sum. But the important part for us is the geometric idea. Second, there is the concept of the convex hull. Given a set of points, we can ask ourselves, what is the smallest convex set that contains these points? In math in general, we mean the whole set. In computational geometry, we are usually only interested in the border of this hull and how to calculate it. You can imagine a rubber band loosely wrapped around the points and then being tightened. When you start with a finite number of points in 2D, this will result in a sequence of straight line segments, forming the border. And it is fairly simple to check whether the line through any 2 points is actually part of this border. If it is, all other points will lie on one side of it. In 3D, it is similar. The convex hull consists of flat pieces, usually triangles. And when we fence off the given points, we can also see that each planar face forming the hull has all the points on one side. Third, a function can be convex. Here the idea is that everything above the function graph forms a convex set. This is typically formalized by looking at 2 points on the graph, taking the segment connecting them directly, and then requiring every point on the segment to be above the function graph. Again, we could write that down in formulas, but the idea is more important. When we are between 2 input values, the graph of the function is below the direct connection between the lifted points. And this is precisely what happens with our paraboloid, and why the inside and outside of the circle correspond to the parts below and above the cutting plane, respectively. When we are between 2 input values, the graph of the function is below the direct connection between the lifted points. As I've said before, this is a really nice statement in and of itself, but probably overkill if you want to construct a circle through 3 points. There is, however, a great geometric application for this, namely to find nice triangulations. Given a set of points from, say, a 3D scan, you might want to see what object you just scanned. To do so, you need to connect nearby points to form a surface. This happens in various forms across medicine, engineering, archaeology, and many other areas. Or take my favorite example, which you might use when creating virtual worlds for movies or video games. If you scatter some points on the XY plane and connect them with triangles, you can then offset their heights to form a terrain. In this case, it's usually preferable for the triangles to be compact and roughly equilateral. When the scene is eventually rendered onto a screen, every detail is represented by tiny square pixels, and the result looks much nicer when the meshed triangles are evenly shaped and do not form narrow slivers. But how would we define triangles in a triangulation to be compact or like bulky? Well, there are 2 ideas for this, and both will give us something called the Delaunay triangulation, named after Boris Delaunay, who studied them in the 20s of the last century. On the left, let's look at a triangle and say when it is part of our triangulation. We include it if none of the other points is within its circumcircle, which makes the triangle compact in a sense. This is obviously what we will use from here on out, since this is precisely the situation we looked at before. Points being in or outside a circle given by 3 points. However, I want to also show you another point of view on the right hand side. Here we have a triangle that is not included in the triangulation. The reason is that it is too narrow. It's a so-called sliver triangle. The angle on the left in particular is very small, and these small angles are what causes the rendering issues I hinted at in the terrain generation example. We want to have large angles, which is another way to see a triangle as compact. Now, as I said, we will look at the condition on the left, but I want to highlight both of them. Firstly, while the left is easier to work with, the right feels more like a justified motivation to me. Secondly, you might encounter either of them when reading about the Delaunay triangulations. Thirdly, I don't want to simply say, hey, this new concept is defined by exactly the thing we just looked at. What a coincidence! So let me really quick motivate how these ideas give rise to the same triangulation. When building the triangulation, you will inadvertently get quadrilaterals, and then have to decide which of the diagonals to use to subdivide it into triangles. Assume that the 4 points happen to lie on a circle. Won't happen in practice, but let's start here. When we look at the angles of the quadrilateral, the opposite pairs both sum to 180 degrees, which is equivalent to the 4 points lying on a circle, and this follows from the inscribed angle theorem. In this case here, we could use either diagonal. If we now assume that one of the points lies inside the circle, its attached angle, and therefore the corresponding angle sum, will get larger, while the other angle sum gets smaller. Since we want to avoid small angles in our triangulation, we should cut the large pair in half by adding a diagonal, not the angles that are already small. When the 4th point is outside the circle, however, we have the opposite situation. It and its partner form the pair of small angles, and we should use the other diagonal. And this is where the two conditions we had before meet. If a point is outside the circumcircle of a triangle in our triangulation, it means its angle pair was small and shouldn't be cut. With that, we can go back to our paraboloid. For finding the Delaunay triangulation for a set of points, we have to determine whether 3 points should contribute a triangle. And we just saw that that means we have to check whether another point is in or outside the circle through this triple. Before that, we have seen that we can lift those points up to the paraboloid and then look at the plane through those lifted points. And when we do that with the point we want to analyze, we have seen that the check to see if it is outside the circle turns into a check to see whether it lands above the plane. This has to be true for all other points too, of course. All lifted points have to be above this plane. That means in particular that all these other points are on the same side of the plane. If you recall, that was precisely the characterization for a plane making up the convex hull. So with our correspondence between circles in 2D and planes in 3D, we get that a triangle is part of the Delaunay triangulation if, after lifting, the respective plane is part of the boundary of the convex hull of the points. In other words, if we calculate the convex hull of the lifted points and project down again, we get a Delaunay triangulation. Well, sort of. When we look closer, we see that we have an issue with some facets. Remember when we did a slight generalization? Our lifted circle check requires that we determine whether the points are above the planes, while the convex hull takes all planes where the points are on the same side, above or below. We can fix that by looking at the outward facing direction of each facet of the convex hull, which we do anyway since we have to check on which side the points lie. And then we discard the facets where this outside direction is pointing upwards. This lower portion is what gives us the desired triangulation. Let's do this one more time from start to finish. If you have a bunch of points for which you want to find the Delaunay triangulation, you start by lifting them onto the paraboloid x squared plus y squared. Then you can immediately forget the paraboloid again. Next, you compute the convex hull of the lifted points, remove the triangles which point upwards, and project the remaining triangles down. This will give you a triangulation of the initial points that is as nice as possible, at least with respect to the conditions I talked about a few minutes ago. Now, some of you might have noticed an issue. I haven't actually told you how to calculate the convex hull here. I only gave you the abstract characterization for when a triangle is part of the convex hull. But checking all triples of lifted points and their triangles is, of course, just as easy or difficult as checking all triples of the original 2D points and their circles. Replacing the Delaunay triangulation problem with a convex hull problem means, first and foremost, that every algorithm one might find for the latter can immediately be used for the former. And calculating convex hulls is a very common task in computational geometry, so that many code libraries will have solutions for that. So you don't need additional procedures for the triangulations. Moreover, it's always nice to have a way to translate between different problems, statements and applications, since it might reveal deeper insights in the future. But our lifting trick does in fact make things a bit easier to calculate. To wrap up this video, let me show you how. We want to know whether a point is inside or outside a circle. That's a common question, not only when trying to find the Delaunay triangulation. The simplest way to check is to calculate the distance of the point in question to the center of the circle and compare that to the radius. Alas, we don't know the center and radius. Our circle is given by 3 points on it, and it's not immediately clear how to find formulas for center and radius from the 3 given points. We can do that, of course, but we can make a slightly simpler calculation. To do so, we have to take a step in a different direction first. Assume you have 3 points in the 2D plane, and you want to know whether they lie on a common line. If you know their coordinates, you can do that by checking if this determinant here is 0. If you don't know what a determinant is, don't worry too much. For the video here, all you need to know is that it's a very specific formula, that it is well studied, and understood why the formula looks the way it does. The more interesting further connection here is to homogeneous coordinates. I made a video about projective geometry, link below and in the corner, where I explained in detail how adding a 1 as a third coordinate helps resolve issues in geometric calculations. And this determinant check here is a direct consequence of what you can find in that video. Here, we will be fine by just knowing that something like this is true. If you know how to calculate determinants, try to prove it in general. Or, maybe a bit nicer, check that it works for the other parabolic lifting from the start of the video. In any case, when we have 4 points in 3D space and want to check whether they lie on a common plane, we can do the same. We need a 4x4 determinant for that, which has a similar but more complex formula than the 3x3 version from before. Again, not super important here, beyond the fact that it is an explicit expression. Of course, we don't want to check whether 4 points are coplanar. We want to check whether 1 point lies above the plane, given by 3 other points. Moreover, we don't have arbitrary coordinates, but points lifted onto the paraboloid. All the work we have done in this video, we now know that this determinant checks whether the 4th point lies outside the circle given by the first 3 points. To be precise, the point is outside when the determinant is negative, at least when we use this precise order of the points. The first 3 must be counterclockwise along the circle, and the 4th one is the one we want to check. It's a quirk of how determinants work, but the worst case scenario is a sign flip error. All in all, the whole lifting plus convex hull machinery might feel just like a neat geometric trick to transfer the problem of finding Delaunay triangulations to a different domain. But the fact that circles in 2D and planes in 3D are inherently linked is, in my opinion at least, a fascinating and surprising insight, as is the final result here, that this determinant is what we should think as the algebraic formula for a circle given by 3 points. If you are familiar with determinants, you can even find the center and radius of the circle from here, but I will leave that as a homework. With that, thank you for watching and until next time.